Right now, as you watch this, there's a very good chance that your processor, the most powerful piece of hardware inside your computer, the component responsible for running every single thing you do, is not fully awake. Not because it's broken, not because something went wrong during manufacturing, but because Windows made a deliberate decision to put part of it to sleep, quietly, automatically, without telling you and without asking whether that was actually what you wanted. While you've been gaming, editing, rendering, working, multitasking, while you've been wondering why your system feels like it's holding back, like it has more to give but something is throttling it, a feature buried so deep in Windows that most people will go their entire computing lives without encountering, it has been managing your processor cores like a night security guard, switching off lights in rooms nobody's using. Except the rooms weren't empty, you were in them, and the lights needed to stay on. Let's fix that. But first, let's make sure you understand exactly what's been happening, because once you see it, you'll never think about your CPU the same way again. Let's start with the basics, because understanding what CPU core parking actually is gives you the context to understand why it matters and why Microsoft implemented it the way they did. Modern processors are not single-core devices. Even entry-level consumer CPUs today come with multiple cores, 4, 6, 8, 12, 16 or more, depending on the specific processor generation and product tier. Each core is essentially a separate processing unit capable of independently executing instructions. Having multiple cores means your processor can genuinely do multiple things simultaneously, rather than just switching between tasks so rapidly it creates the illusion of multitasking. Real parallel processing, real simultaneous execution, distributed across multiple independent units. That's what a multi-core processor provides. Core parking is a power management feature built into Windows, specifically implemented through the Windows Power Management infrastructure, which communicates directly with the CPU's hardware power states, that allows the operating system to deliberately place individual cores into a low-power idle state when the system's current workload does not appear to require them. The idea behind it is straightforward and, on the surface, reasonable. If your computer is running a lightly threaded task that can be handled by 1 or 2 cores, why keep all 16 cores fully powered and ready to go? That consumes more electricity, generates more heat, and potentially shortens component lifespans. Parking the unused cores, putting them into a deeper idle state where they consume significantly less power, sounds like sensible resource management. And for certain use cases, it genuinely is. On a laptop running on battery power during a light workday of email and document editing, core parking is doing exactly what it was designed to do, conserving energy intelligently to extend battery life in a context where maximum performance is not the priority. Nobody watching a YouTube video on battery power needs 16 fully awake processor cores standing at attention. The feature, in that context, makes complete sense, and arguing against it, in that context, would be arguing against something that genuinely serves the user's interests. But here's where the story turns into something far more consequential for a large number of users, particularly those using desktop computers, those gaming, those running creative or professional workloads, and those who have specifically chosen a high-performance power plan because they want maximum performance from their hardware. Because core parking, in its default Windows implementation, does not restrict itself to battery-saving scenarios. It doesn't automatically switch off when you're running demanding software. It operates according to a set of thresholds and timing behaviors that, in many configurations, cause cores to be parked even during workloads where those cores are genuinely needed. And the latency introduced by unparking a core that needs to wake up and become active again can create subtle but real performance penalties that manifest as stuttering, inconsistent frame rates, spikes in input latency, and the general feeling that your system is fast when it's running smoothly but inconsistently so in ways that are difficult to pin down. This is the specific pattern that has made core parking a topic of deep frustration and investigation in gaming communities, video production communities, and among audio professionals working with digital audio workstations. In each of these contexts, the workload has specific characteristics that make core parking particularly problematic. Gaming is highly latency sensitive. The difference between a core being immediately active and a core needing to wake up from a parked state can contribute to microstutter and frame time inconsistency in ways that raw average frame rates don't capture. Video editing and rendering software frequently needs to burst quickly across all available cores when processing certain operations. And digital audio workstation software is perhaps the most sensitive of all. Audio dropouts and buffer underruns in music production software can occur specifically because a core needed for audio processing was parked at the exact moment the audio engine required it, creating an audible glitch in what should be a seamless recording or playback session. These aren't theoretical edge cases. They are reported extensively by real users in real technical environments who have specifically traced performance inconsistencies back to core parking behavior through systematic testing, benchmarking with cores parked versus unparked, capturing frame time data, measuring audio latency under both conditions, and documenting statistically significant differences in performance consistency between the two states. The improvements from unparking cores are not universal and not always dramatic in terms of raw maximum performance numbers, but in terms of consistency, stability, and the elimination of intermittent stuttering and latency spikes, the documented improvements in appropriate use cases are real and measurable. Let's dig into the technical mechanics a bit more, because this is where the story gets interesting from an engineering perspective. Core parking works in conjunction with something called C states, processor power states, defined by the Advanced Configuration and Power Interface Standard, commonly known as ACPI, which governs how processors communicate their power state to the operating system and vice versa. C0 is the fully active state. The core is running, executing instructions, fully powered. C1 through progressively higher C state numbers represent increasingly deep idle states, where the core saves progressively more power by shutting down progressively more of its internal circuitry. C6, which is the deep power down state used by many modern desktop processors during parking, involves shutting down the core's voltage entirely and saving its state to a local cache, achieving dramatic power reduction, but also requiring a meaningful transition period to exit when the core is needed again. The transition time from a deep C state back to C0, from fully parked back to fully active, is not enormous in absolute terms. We're talking about microseconds to low milliseconds in most cases, but in contexts where consistent low latency response is critical, gaming, audio processing, real-time rendering, even small inconsistent delays, and when a core becomes available, can compound across multiple frames, multiple audio buffers, multiple rendering passes, into something that is perceptible to the user as inconsistency, even if no individual incident is measurable by human reflexes alone. Frame time variance, the irregularity in how long each individual frame takes to render, even if the average frame rate looks acceptable, is the metric where core parking's effects tend to surface most clearly in gaming scenarios. Now, here's something that makes this more complex and more interesting than a simple parking cores is bad, unpark them all narrative. The relationship between core parking and the Windows power plan you've selected. Windows ships with several built-in power plans, and the behavior of core parking differs significantly between them. The balanced power plan, which is the default for the vast majority of consumer Windows installations, implements core parking aggressively, meaning cores park quickly when not in active use, and the thresholds that trigger parking are relatively low. The high performance plan reduces, but does not eliminate core parking in many configurations. And the ultimate performance plan, which exists in Windows 10 and Windows 11, but is not available in all editions, and may not appear in the standard power plan selection without being specifically enabled or unlocked, is designed to minimize power management interference with performance, including significantly reducing core parking behavior. Here's the critical detail that most people miss. Even on the high performance plan, core parking is not fully disabled by default in the standard Windows configuration. This surprises many users who assume that selecting high performance means they have disabled power management features that might throttle performance. The actual behavior of the high performance plan is more nuanced. It raises the minimum processor state, reduces the aggressiveness of several power saving features, and decreases the tendency of the processor to scale down its clock speed. But it does not automatically set the core parking minimum to 0%, which is the setting that actually ensures all cores remain active and available at all times. Let's talk about where exactly these settings live in the Windows configuration, because this is genuinely buried, and is something most users have never seen even after years of using Windows. The core parking settings are not in the main power options window. They're not in the visual interface that most users interact with when switching between balanced, high performance, and other power plans. They exist in the advanced power settings, specifically in a section of the power plan's advanced properties related to processor power management, and within that, a subsetting called Processor Performance Core Parking Options, including minimum and maximum numbers of unparked processors, which Microsoft expresses as a percentage of total logical processors. By default, even on high performance, that minimum value for unparked processors can be set to something less than 100%, meaning that, at its minimum, the system is configured to potentially park down to a portion of your available cores. Raising this minimum percentage, ideally to 100%, is the actual configuration change that fully disables core parking's tendency to reduce the number of active cores under light load. And this is something that requires deliberately navigating into the advanced power settings, into the processor power management subsection, and manually adjusting a value that is not surfaced in any visually prominent way in the standard Windows settings interface. There's also a more direct route that bypasses the graphical interface entirely and operates at a lower system level, specifically the Power Configuration command line tool built into Windows, which allows you to set specific guide-referenced power policy values directly from the command line. The guide associated with core parking, specifically the minimum number of unparked processors setting, can be set to its maximum value through a simple command line instruction, affecting the current power plan immediately without requiring navigation through multiple nested menus. This method is preferred by many technically proficient users precisely because it's explicit, documentable, and not dependent on navigating menus that may look slightly different across Windows versions or between machines with different OEM configurations. Let's now talk about something important that often doesn't get mentioned in conversations about unparking cores: the relationship between core parking and your specific processor architecture, because this matters enormously for understanding how significant an impact unparking will actually have on your particular machine. Not all CPUs are equally affected by core parking behavior, and understanding your specific hardware helps set realistic expectations about what you will and won't notice after making this change. On processors with a uniform core architecture, where every core is functionally identical, the parking behavior and its effects are relatively straightforward. Cores are either awake or parked, and the performance difference of having more or fewer cores available is primarily a function of how well your workload utilizes parallel processing. But on newer processors featuring a hybrid architecture, most notably Intel's 12th generation, and later core processors featuring a combination of performance cores and efficiency cores, abbreviated P cores and E cores, the interaction between core parking and the task scheduling system becomes more complex. Intel's Thread Director technology, working in conjunction with Windows 11's scheduler, is designed to intelligently assign tasks to P cores or E cores based on the nature and priority of the workload. Core parking behavior that interferes with this assignment process can, in some configurations, produce more noticeable performance irregularities than on uniform architectures, because the system's ability to route high-priority tasks to the highest performance cores can be impaired if the scheduler's expectations and the parking state of specific cores are misaligned. AMD's Ryzen processors, particularly those built on the Zen 3 and Zen 4 architectures, have their own relevant consideration here. AMD's Precision Boost algorithm, which manages dynamic clock speed and power state adjustments at a hardware level, interacts with Windows power management settings, including core parking, in ways that have been extensively studied by the overclocking and enthusiast community. For Ryzen users, simply unparking cores through Windows power settings is often one part of a broader optimization picture that includes correctly configuring AMD's own power management software, choosing appropriate power plan profiles, and in some cases, using AMD-specific plans that are specifically designed to avoid conflicts between Windows power management and AMD's own hardware-level performance management algorithms. All of this is to say, unparking your cores is a meaningful, well-documented performance optimization for many users, but it sits within a broader system that includes CPU architecture, power delivery, thermal management, and the specific nature of your workloads. The most important thing to understand is that it's not a magic universal fix that doubles everyone's performance. What it is, and this is the accurate defensible claim, is the elimination of a specific Windows-imposed behavioral constraint that, in certain contexts and workloads, creates measurable performance inconsistency that the user did not knowingly choose to accept and that they may not even realize is there. Now let's walk through exactly how you actually do this, step by step. Because the point of knowing about this is being able to act on it, and the specific process matters. The first approach is through the Graphical Power Options interface. Start by opening the Control Panel, not the Settings app, because some of these options are only fully accessible through the legacy Control Panel interface. Within Control Panel, navigate to Hardware and Sound, then Power Options. Here, you will see your available power plans. If you're on the High Performance plan or the Balanced plan, click on Change Plan Settings next to your active plan, and then on the next screen, click Change Advanced Power Settings. This opens the Advanced Settings dialog box where the deeper configuration options live. Within this dialog, scroll down until you find Processor Power Management. Expand that section. Inside, look for Processor Performance Core Parking Min Cores and Processor Performance Core Parking Max Cores. The min cores value is the critical one. This sets the minimum percentage of logical processor cores that Windows must keep unparked at all times. If this value is set to something below 100, Windows is permitted to park cores down to that percentage floor. Setting the minimum to 100%, both on battery, if applicable, and plugged in specifically, tells Windows that it must keep all cores fully unparked and active at all times under this power plan. Important caveat here, On some Windows installations, particularly with certain OEM configurations or certain Windows versions, the processor performance core parking options may not be visible in this dialog by default. Microsoft has, in certain configurations, hidden this section of the advanced power settings from the standard view. This is where the command line approach becomes not just an alternative, but potentially the only direct route. The command line method, run in an elevated command prompt or PowerShell window, uses the PowerCFG command with the GUID that specifically references the core parking setting. The specific command that sets the minimum processor performance core parking value to 100% for the current power scheme, ensuring all cores remain unparked, is accessible through this interface regardless of whether the graphical menu shows the option or not, because it operates at a level below the graphical interface layer, writing directly to the power policy configuration that Windows stores and applies at the system level. For users who want to verify the change has actually taken effect after making this adjustment, there's a specific way to observe core parking status in real time. Task Manager, while useful for many things, does not directly show you the parking state of individual cores. For that, you need either the Resource Monitor application, which can be opened from a Task Manager's Performance tab, or a third-party tool specifically designed to display per-core activity and parking states, of which several reliable free options exist in the PC enthusiast and system monitoring tooling ecosystem. Seeing all cores showing active state and responding to load, rather than some cores showing minimal to no activity even under demanding workloads, is the clearest visual confirmation that the parking change has taken effect and is influencing your system's behavior. Let's talk about power consumption implications, because one of the legitimate concerns people raise when discussing disabling core parking is the impact on electricity usage and heat generation. Keeping all cores fully active and unparked does mean the processor consumes marginally more power at idle, because the deeper idle states that parking enables are no longer being used. However, it's important to put this in perspective for desktop users specifically. The additional power draw from keeping cores unparked at idle is relatively modest compared to the total system power consumption. And for a desktop machine that spends most of its time either under meaningful load or in a full system sleep state, the practical impact on electricity bills is minimal to negligible for the vast majority of users. The power-saving argument for core parking is genuinely meaningful for laptop users on battery power. And for laptop users, the recommendation would be to apply unparking specifically to the plugged-in configuration while preserving parking for the on-battery configuration, getting performance benefits when connected to power while maintaining battery efficiency when not. Thermal implications follow a similar logic. Keeping cores unparked does not mean the processor runs hotter under sustained load, because the maximum thermal output is determined by the workload, not the parking state. What it means is that idle temperatures may be very slightly elevated compared to a deeply parked configuration, since the cores are in a higher energy idle state. For systems with adequate cooling, this difference is functionally irrelevant. The processor runs at full load temperatures during demanding workloads regardless of parking state. And at idle, the temperature difference from unparking is unlikely to affect component longevity or system stability in any meaningful way. Let's now address the gaming performance angle specifically, because this is where the most concrete, most widely documented, and most practically significant improvements from core unparking have been reported. The gaming scenario is worth dedicating specific attention to, because it illustrates most clearly why the default Windows configuration is ill-suited to this use case. Modern games are increasingly multi-threaded, designed to distribute their computational workload across many CPU cores simultaneously. When a game's engine needs to spawn threads across multiple cores, it expects those cores to be immediately available. When a core is parked, responding to a new thread assignment involves a latency penalty for the core to exit its low-power state and become ready for execution. In a gaming context, where frames are being rendered in windows of 16 milliseconds or less for 60 frames per second gameplay, and 8 milliseconds or less for 120 frames per second, even small latencies in core availability can contribute to frame time variance that manifests as micro-stuttering, the subtle but perceptible inconsistency in visual smoothness that experienced gamers feel as jank, even when the average frames per second counter looks perfectly acceptable. Frame time graphs, the actual measurement of how long each individual frame took to render, plotted over time, tell a more complete story of gaming performance than raw average frame rates, and it's in frame time consistency data where the effects of core parking and unparking show up most clearly. Testing across a variety of games and hardware configurations has consistently shown that frame time variance tends to decrease when cores are unparked, even when average frame rates remain similar between the two configurations. This means the experience of playing the game becomes smoother and more consistent without necessarily seeing a dramatic jump in the peak frame rate number. which can be counterintuitive for users who evaluate their performance solely through the frames per second counter in the corner of their screen. Input latency is the other critical metric in gaming that connects directly to core parking. The time between you physically moving your mouse or pressing a key and that input being processed and reflected in the game is affected by how quickly the system can respond to the input event, which in turn can be affected by core availability at the exact millisecond the input occurs. Studies measuring end-to-end input latency in gaming systems have identified Windows power management settings, including core parking behavior, as among the configuration variables that can meaningfully influence input lag measurements, particularly at the low end of the latency spectrum, where the differences between responsive and unresponsive systems are most noticeable during high-speed, reflex-dependent gameplay. For competitive players, content creators streaming and gaming simultaneously, and anyone for whom both visual smoothness and input responsiveness are priorities, core parking is one of the legitimate Windows internal configuration changes, not overclocking, not hardware modification, not third-party software, that can move the needle on these specific performance characteristics without introducing instability risks. Let's now address something important for users who might be wondering whether there are third-party tools that manage this for them, because there are several well-known options in the PC optimization community, and they deserve an honest assessment. Tools that market themselves as core unparkers or PC optimizers, and specifically address the CPU core parking setting by automating the power CFG changes or directly writing the relevant registry and power policy values, have existed in the Windows enthusiast community for years. Some of these tools are legitimate, focused, and do exactly what they claim, applying the relevant power management configurations without installing additional software, creating persistent background processes, or making other changes to your system beyond the specific task of managing the core parking setting. However, the PC optimization tool category as a whole also contains a significant number of applications that go far beyond core parking adjustments, bundling unnecessary system modifications, launching persistent background processes that themselves consume the resources they're claiming to optimize, and in some cases, including genuinely problematic software alongside what they advertise as their core functionality. The recommendation here is direct. The Power CFG command line method and the Control Panel Advanced Power Settings interface are both built into Windows, require no third-party software, and accomplish the core parking adjustment completely and verifiably on their own. For this specific task, there is no compelling reason to install any additional software, because the native Windows tools are entirely sufficient, and their behavior is fully transparent and documentable. Let's bring this full circle now, because there's a bigger idea here that this specific optimization illustrates about the relationship between users and the operating systems they use every day. Core parking is a feature implemented by Microsoft with a genuine, legitimate purpose: power efficiency in scenarios where that trade-off serves the user's interests. Nobody is disputing that, but it was implemented in a way that applies broadly across use cases where the trade-off doesn't serve the user's interests. And it was buried deep enough in Windows configuration layers that the vast majority of users, subject to its effects, have never been given the opportunity to make an informed decision about whether they want it applied to their system. This is a pattern, not a conspiracy, not malice, but a consistent pattern of defaults that favor Microsoft's operational and efficiency narratives, systems that behave in ways that reduce support complaints about power consumption and heat, systems that work reasonably well for the average light workload user, without necessarily being configured for the significant population of users who have specific, demanding performance needs and who would absolutely choose differently if the choice were clearly presented to them. The high-performance power plan should disable core parking by default. For a user who has made the deliberate choice to select a plan literally named high performance, the expectation that their CPU cores will be fully available without additional configuration steps buried in legacy control panel menus is completely reasonable. And Microsoft's failure to meet that expectation is a genuine usability and transparency gap. The ultimate performance plan gets closer to appropriate default behavior for demanding users, but it isn't visible in all Windows editions and doesn't appear in the power plan selection without deliberate steps to enable it. Another example of the right option for many users, existing but not being readily accessible. Your CPU has capabilities you've been paying for and not fully accessing. The cores are there. They were there when you bought the machine. They have been sitting in Windows-managed sleep states during the exact moments you needed them most. The frame that stuttered, the audio buffer that dropped, the render that hesitated, not because your hardware isn't capable, because a default setting you didn't know existed was making decisions about your hardware on your behalf, optimizing for a priority you didn't set. In a scenario, the engineers who designed the feature weren't necessarily imagining when they picture your actual use case. One setting, one adjustment. And your processor wakes up completely for the first time since you installed Windows. That's not an exaggeration. That's just what happens when you stop letting the operating system manage your hardware for its own reasons and start managing it for yours. Go wake your CPU up. It's been sleeping long enough.